Hello, stat students. Today we are going to finish chapter 3 by talking about 3.2D, reading computer outputs, so we can come up with regression line and important pieces of the regression equation. There are several different outputs that you can be presented with, and that's via graphing calculator. You can have some software such as Fathom, which students can get for a fairly cheap price. Minitab is super expensive, and then there's one called Jump. Every these software programs have their limitations, and some are better than the others, and so on. But the main thing is we need to be able to read them and interpret them in order to get the important information that we need. So let's look at several examples to see if you can find the information. The first one is body weight and pack weight. And so if you look at this is from a Minitab output. You have several pieces of information here, some of which you can ignore and some of which you don't want to ignore. Now, body weight and pack weight, your body weight is given right here as the explanatory variable. Oops. Mm, go. And then the slope is right here. So okay, the constant tells you that's your y-intercept. So this is your y-intercept. Go. And you do not need to know the last three columns because that is something we do in second semester when we do statistical tests. So you have your t values, your p values. All right, and then the bottom, the first number right here, this is your standard deviation of the residuals. Standard deviation. Okay, and this, of course, is r squared. And you don't need to worry about r squared adjusted. So those are all the pieces of information that you need to do questions 1 through 4. What is the equation for the regression line? So in terms of context, which is what we want, instead of writing y hat, and you can write y hat, I sometimes do this. So I know that the response variable is pack weight, but it's the predicted pack weight. So make sure you show that's predicted by putting a hat over that is equal to the y-intercept, so 16.265, plus the slope, which is 0.9080, move that, times the explanatory variable, which is body weight. And so that basically takes care of it in context. And you could totally write, if it doesn't say any of that, you could have just written y hat equals 16.265 plus 0.9080 times x. It's always good if you are asked to do something in context to do it the first way. What is the typical prediction error? So the typical prediction error, that's your S. So S is equal to 2.26954 pounds of pack weight, your response variable. Right? What is the coefficient of determination? So R squared is equal to 63.2%. Okay. And what is the correlation? Remember, correlation is not given, but correlation is the square root of the coefficient of determination. So R is equal to the square root of the proportion, which is 0.632. If you find the square root of that, R is equal to 0.795. And that is how you read a Minitab output. Here's a second example. And goes back to our used Hondas. What is the equation for the regression line? So I guess we can identify everything. So this is your X variable. Cost, remember, was Y. Okay. So it would be cost, predicted cost is equal to the y-intercept plus, which is going to be a minus 86.18 times the miles driven. Okay. The typical prediction error would be S equals 971.647. There we go. And then the coefficient of determination, R squared equals 76.4%. And the correlation, the square root of that, so 0.764, R equals 0.874. All right, and the last one, and this is the one that's like hardest to read, is from the jump output, and it's age and reading scores. So age is your explanatory variable here. Okay. Kind of, instead of giving you a constant, they actually use the word intercept. So that's kind of easy. So then you know that's dealing with y. So that part's not bad. This is your slope right here. If the top number is going to be your y-intercept. And then the other things, r squared up on top, you know, r squared adjusted, you don't need to worry about. The root mean square error is actually S. And so this is the standard deviation of the residuals. Don't need to know mean of response or observations of all that other junk or standard error, T ratio. Again, that's stuff you use in second semester. So the equation for the regression line is the predicted reading scores is equal to your y-intercept minus 1.126989 times the age. Okay, the typical prediction error is 11.02291. And that would be like your reading score. Coefficient of determination would be r squared. So r squared is equal to 0.409971. And we're going to change it. Or you can leave it like that, or you can do a percent because it's easier to interpret. Okay, and the correlation, square root of 0.409971, which happens to be 0.640. And that's how you read some computer outputs. All right, to round off the end of the chapter, we are, let's see, sorry, we're not done yet. So correlation and regression wisdom here. Correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, be aware of their limitations. If you look at the graphs below, it's the same variables, but the variables are plotted on different axes. So in the first graph, you have the NEA change, the non-exercise change on the horizontal axis, and fat gain on the vertical axis. And then on the other graph, it's reversed. So if you look um, on the far right or on the top, the S and the R squared, or the S is different, but the R squared is the same, and so is, you don't need to worry about the R squared adjusted. But basically, what it's saying is the correlation doesn't change if you switch the response variable and explanatory variables, but other things do change. The graph has dramatically changed. So just make sure that you're very aware of the variables when you're making a scatter plot, that you have the explanatory variable correct and the response variable. It's really important when you're doing regression. All right. Correlation and regression lines describe only linear relationships. Be careful about calculating without graphing the data. All of the data sets below have a regression equation of y hat equals 3 plus 0.5x. So this is on page 188 if you have a book. If you look at the first one, and they all have the same correlation. Okay, so if you look at the first graph, it's linear. Okay, linear model. Second one is curved. Third one, you have an outlier. And the last one, you have all these points right here, but then you have a point out here that's far right or left of everything else. So this is an influential point. So basically, this example is just saying, make sure that you're careful about calculating without graphing, or be careful about calculating without graphing the data. Correlation and least squares regression lines are not resistant. So this is just the good old wisdom here. And the reason why they're not resistant is because they involve the mean and standard deviation. Okay, now we're at the very last thing. So, and I mentioned this before in the chapter, that correlation does not imply causation. So, association does not imply causation. An association between an explanatory variable x and a response variable y, even if it is very strong, is not by itself good evidence that changes in x actually cause changes in y. Because, and you're going to learn this in the next chapter, causation can be explained when there is an experiment So an experiment, a good experiment would be having random treatments, having a control group, and so on, so that lurking variables can be managed. And we'll learn all about this in chapter 4. So let's take a look at an example here. A serious study once found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars is even better, and so on. There is a substantial positive correlation between number of cars X and length of Y. Why? Well, if we think about it, there's income that's involved. So when you have more money, you tend to be have access to better medical care. You can be better educated, and so on. And all of those things, imply that you would live longer. So, income, better educated, better medical care. But that doesn't mean that one is that because there's a strong correlation that that's causing it. Right? And that is the end of chapter 3. Have a great day, students.